Hello everyone, myself Tellam Rambabu. Today in this video I will explain one lab of digital signal processing laboratory, one experiment. Here I will explain experiment 3. Let's proceed. The main objective of our experiment is find magnitude spectrum of a signal sampled at 25 Hz using DFT algorithms. In this we will use matrix representation of DFT to compute DFT coefficients for a given signal with a duration of 3 seconds. And compute period of the signal and compare with autocorrelation based period estimation. Like we will do these two experiments. Like we will find the period by using DFT algorithm and by using autocorrelation algorithm. So first let us discuss what is discrete Fourier transform. The frequency samples that are obtained by evaluating the Fourier transform x of omega at set of n equally spaced discrete frequencies is called the discrete Fourier transform. This is the input, this is the equation between the input and output. Here the output is DFT, means the coefficients of the DFT, and this is the given input is x of n signal. Here we are finding n point DFT. The main difference between the discrete Fourier transform and discrete Fourier transform is DTFT, means discrete time Fourier transform, is continuous in nature with period of 2 pi. So many in general we will apply this Fourier transform to analyze the signal. So in practical sense we cannot analyze the continuous discrete time Fourier transform in a digital system like computer or anything. So we need to discretize it. We need to sample the frequency response of the signal. So here a discrete Fourier transform comes into picture. It is the frequency sample that are obtained by evaluating Fourier transform based generally DTFT at set of n equally spaced discrete frequencies. The relation which allows us to recover the sequence is called the inverse discrete Fourier transform. This is by using this relation we will get our x of n by using the coefficients of discrete Fourier transform. Here DFT has a linear transformation. If you observe clearly, we can write the same previous equation by using like this. This is the DFT equation. This is a IDFT equation. Here summation n equal to 0 to n minus 1 x of n into w or omega of n kn, where w of n is its nth it is this e power minus j pi minus 2 pi by n, and here k runs from 0 1 2. This is, and this is synthesis equation 1 by n summation k equal to 0 to n minus 1 x of k into w of minus kn. Here minus is there, so I am keeping here minus. If you observe clearly, for n equal to 4 we can express the same previous equation by using this. Here our n equal to 4, so I am replacing capital N with 4. If you want to find capital X of 0, just put small k equal to 0. If you want to find capital X of 1, just keep k equal to 1. Similarly, k equal to 2, k equal to 3. If you observe, when I keep k equal to 0, I will get this equation. By keeping k equal to 1, we will get this equation. By keeping k equal to 2, we will get this. If you observe clearly, we can write or we can manipulate or we can rearrange the above 4 equations in a matrix form. This is our input signal x0, x1, x2, x3, and this is the matrix. This is one vector, this is one row, another row vector, this another row vector, this another row vector. This first row vector into this signal will give x of 0, this second row vector and this gives x of 1, this third into this signal gives x of 2, this into this will get x of 3. Basically it is a linear transformation of x with the W matrix. Upon W matrix gives rise to DFT, where W is, you will get W by W as e power minus j 2 pi by n into nk. I can write the same linear transformation using this. W into signal gives rise my discrete Fourier transform. If I want to compute this small x of n, I can use this relation, where here W inverse is just just like transpose and a complex conjugate of this matrix. Now let us understand our Arduino and MATLAB codes. First we will understand by using autocorrelation, then we will study by using DFT. This code actually I explained previous itself. Like last week I explained the same code. So first I will explain the DFT code, then I will come for autocorrelation. Just give me a few seconds. This is our input signal with as I mentioned earlier, the sampling frequency is 25 and I am taking for 3 seconds duration, so to my the length of my signal will become 75, and here I am declaring some variables. Here in this Arduino code, since I need to do by using the using matrix representation, so I will compute the W term in two matrices, like one is real component and another is a complex component. Since in Arduino we cannot use directly complex number, so I am dividing my W matrix into real part and imaginary part. In real part I will just find the cos terms, cosine terms. In imaginary part I will find the sine terms. Okay, this is my W real where I will find cosine terms. This is my W imaginary where I will find sine terms. And this is my capital X of 1 is my Fourier DFT. So first before going to do apply the DFT, first I will declare these variables. First I will declare the some variables and first I will do moving average filter. Okay. So this is my W matrix. For calculating W, we just has K and N. K is N sufficient. So and one more thing is here W of K into N is same as W of N into K. So there is no need to compute both. If you observe clearly, this W, this and same, this and this and same, this and this and same, like this and this is same. Like the W matrix is symmetric with respect to diagonal. So I will compute only first these only half of my W matrix, means I will compute for n into n plus 1 by 2 terms. Then I will apply. Then I will compute these below terms. Okay. After calculating by using Arduino, then we will calculate by using MATLAB also. This is how. So here I am calculating the W real terms. Here cos of 2 pi into k into n. I am just running my k equal to 0 to n minus 1 and n equal to k to n, because I mentioned earlier my W matrix is symmetric with respect to diagonal. So I can just replace the W of k into n is same as W of nk. Similarly, this imaginary part. After calculating that, first I will smooth my signal. This is moving average filter. I am padding some zeros to maintain length equal to capital N only. Then I want to calculate just I want to calculate capital X. Like I want to multiply my column, my signal with W. So I am just doing here that, and I want to plot magnitude spectra. So I am finding its magnitude of the x1. This x1 is the magnitude of my DFT signal. Directly I am finding square root, and this is a square plus b square. Okay, this is real part square plus imaginary part square, and I am applying square root. After finding my spectrum, I will find the maximum frequency component, so that I can find the frequency in the signal. So this is the code for finding the maximum frequency component. First I am assuming my x of 0 is maximum. I will check in my x of 1. If I find something is maximum, I will just replace maximum with that. This is the coefficient maximum. This is the index of the maximum. So if I want to find the frequency, maximum frequency, this my I into fs by n. This will give my maximum frequency, and this will give my beat per minute. Like since my signal is here ppg signal, so I am calculating beats per minute. Beats per minute is 60 into frequency. So let's see what is our beats per frequencies. Here I am getting my beat per beats per beat by is 60 beats per second by using DFT. Let us see what we will get by using autocorrelation. The autocorrelation code I am not going to explain because I explained last time itself. So I will just run my autocorrelation code for the same input, and I will get I will check what is my output. Here I am getting my output as 78 beats per minute. By using DFT I got 60 beats per second. Let us verify what we will get by using MATLAB. This is my same DFT algorithm by using MATLAB. Here I am this is my signal, this is my length of the signal. First I am finding moving average, then I am applying directly. I am applying my I am finding capital X by using e power j terms. Okay, this is W of n, W matrix, and then I am multiplying W matrix with my y, so that I will get here capital X is frequency. So I am plotting its magnitude spectra, and in that magnitude I am finding this maxima. This maxima, the corresponding coefficient is maximum I am getting at L max equal to 4. I am getting maxima, so L max into fs by n will give my frequency of signal. So if I want to find the BPM, this is my BPM is 80 beats per second, 80 beats per minute. I got 80 beats per minute by using MATLAB. So let us analyze our, this is the conclusion. I got beats per minute by using DFT algorithm in Arduino is 60 beats per minute. Same beats per minute by using autocorrelation function in Arduino is 78. So error between these A and B is approximately 23%. When I calculated beats per minute by using DFT algorithm in MATLAB, I got 80. The error between the B and C is 2.5%. It means the mostly the beats per minute is around 78 or 76 something. Okay, thank you. We are done with today's experiment.